This is the first lecture in week 2 of causal inference. So we're going to talk about subclassification and matching first, then we'll get to, matching, but matching in general, and then propensity score matching. So the whole idea here is that we are going to work our way up from basic comparisons of different categories of outcomes, and then thinking about how to start incorporating control variables. First thing we need to talk about is the independence assumption, something we defined last week. The independence assumption is essentially that the expected value or the expected outcome for treated and non-treated individuals is the same because the treatment is randomly assigned. So in math, that's expected value of y1, expected value of y1, they're equal to one another, conditional on treatment assignment. So remember, this one is observed, this one is unobserved. We can also write that as the outcomes are independent of treatment. Remember, that's almost never the case in economic settings unless you have a randomized controlled trial. For instance, no one decides to drink and drive based on a coin flip. No one randomly chooses whether to take up smoking. People don't typically randomly choose to do most things. Instead, people select into things based on observed and unobserved characteristics. So this introduces the selection problem or confounder problem. So we need a stronger assumption, conditional, maybe this is a weaker assumption, conditional independence assumption. So we're assuming now that the outcomes are independent of treatment assignment, conditional on observed X variables or observed characteristics, where X is a vector matrix or matrix of attributes. In other words, X used to be contained in U, but if we take X out of U and control for it, then we're back to some form of independence assumption. Let's look at an example. We have smoking and lung cancer. Our goal is to estimate the relationship between lung cancer and smoking type. We're not actually going to look at a regression. We're going to just look at differences in means across groups. And then we're going to talk about why this can go wrong and how the first way you might think about adjusting for confounders. So this table is death rates per 1,000 people, non-smokers, cigarette smokers, cigar and pipe smokers, different regions. What we notice here, these are raw death rates. Interestingly, non-smokers and cigarette smokers appear to have, at least in the United States, identical death rates. In Canada, they're not much different. So that suggests that cigarette smoking in the US and Canada is not bad for you. In the UK, it's a little bit bad for you. Cigar and pipe smokers, they die more frequently than anyone else. Now, is this true? What could be going on here? We know that's not true. We know cigarettes are bad for you. So what's happening? Why is our incidence of lung cancer, treatments, cigarettes, cigars, and pipes? The independence assumption requires that the outcomes here the expected outcomes are the same conditional on treatment. What's violating this? So in other words, what we've assumed in the previous table is that your smoking preference is exogenous, if we assumed that was a causal relationship. Yeah, we've assumed that the smoking preference is exogenous, or in other words, people randomly select into smoking different types of things. That's obviously not true, but why? If the independence assumption holds and smoking preference is exogenous, then it must also be true that the observable characteristics of the smokers are the same for each category and for the non-smokers as well. For example, it must be the case that people that choose to smoke cigarettes are observably the same as people that choose to smoke pipes and cigars. This is called balance of observables. You may have seen these tables in papers. We create these tables to help show your matching routine is working. Actually, we usually create these tables prior to doing any sort of matching. So we would create the tables to usually in the pre-treatment period to say how similar are the treatment and control groups. And if we find differences across observables, then that's when we start thinking we need to control for those things. So let's look at an example from one of my papers. This is a table of balance. We have a control treatment group. We have means for the control, standard deviations for the control, means for the treatment, and standard deviations for the treatment group. And then mean difference. And what we're looking for here is differences in means across the different groups and whether or not they're statistically different. We know they're going to be slightly different, but are they statistically different? So like, for example, this was a randomized controlled trial, so the pretreatment electricity use, this is prior to treatment, we would expect if it's a randomized controlled trial, the pretreatment electricity use should be not statistically different between the control and treatment group, and that's what we found. 0.84, 0.92, those are different, but they're not statistically different, so that's the important part. Is the income different between the control and treated group? No, they're the same. Education's the same. We found in this case there's only one group that, or one variable for which the control and treatment groups are statistically different. And you can decide whether or not you want to address that. You can control for it, or you can match on it, or do something to deal with it, or you can just argue it's not a problem. Getting back to our smoking example, the question was, why did it look like the death rates for cigarette smokers and non-cigarette smokers were the same? Why did it look like cigar and pipe smokers were especially bad? Well, age. Age is an obvious confounder. Age affects whether or not you smoke, and it also affects whether or not you die. So age is a confounder. So here are the ages, average ages of people in the groups in this study. Non-smokers' average age is 55. A little bit older than cigarette smokers in Canada, but cigar and pipe smokers across the board are older. And so older people are more likely to die, so they're probably more, and they're also more likely to smoke cigars and pipes, so that's a problem. We could draw a DAG to represent this, but at this point, I think you kind of know how this works. Sorry. Subclassification. So subclassification is maybe the simplest way we can think about controlling for a single confounder. And subclassification depends on being able to cut up your confounder into groups. So in this case, we're cutting our age variable into groups, and we're going to reweight our death rates based on the fraction of people within these groups. So what this table is showing is the death rates for cigarette smokers in each age group, 20, 40, and 60, for the 3 different age groups. And here we have the number of cigarette smokers in each age bracket and the number of pipe and cigar smokers in each age bracket. And notice that the distribution of cigarette smokers is different. It's actually exactly the opposite because this is a stylized example, but the distribution is different for the pipe smokers than it is for the cigar smokers. And so we're going to reweight these death rates based on the distribution of cigarette or the cigar and pipe smokers so that we can have a death rate for cigarette smokers that's comparable to the death rate of pipe and cigar smokers. Let's do that. Here we have the death rate based on the distribution of cigarette smokers, 20. This is our death rate for the first category of age times the number of people in that first category over the total number of people, cigarette smokers, plus the death rate in the second age category times the number of people in that age category, plus the death rate in the third category, and so forth. We can go back at our our table and look at exactly how this is calculated. So death rate for cigarette smokers times the number of people in that age bracket. Death rate's 20 times the number of people divided by the total. So this is the death rate for cigarette smokers with the age distribution of cigarette smokers. If we multiply the same death rate, 20, 40, 60, by the distribution of cigarette and pipe smokers, we get a much higher death rate, 51. So we would call this the age-adjusted mortality rate for cigarette smokers, were they to have the same age distribution as cigarette smokers or cigar smokers. So here, this table is showing us the age-adjusted mortality rates for each category in each region. And this looks a lot better. This follows our intuition that cigarette smoking is bad. It's worse than not smoking. Cigar and pipe smoking actually looks not too bad. You may or may not believe this. There might be other confounders that are left out, but just looking at age-adjusted mortality rates, this conforms with some intuition or what we know from medical studies that cigarette smoking is bad. And this is basically what control variables are doing. And of course, that begs the question, which control variable should we use? And we'll get to that. Let's do a quick review. The set of controls should satisfy the backdoor criterion and close all backdoor pathways. However, the controls must not be colliders. We've talked about that. We have our identifying assumptions, the conditional independence assumption. The outcomes need to be independent of treatment, conditional on observables. The probability of treatment, conditional on observables, has to be between 0 and 1. This means we need common support over X for the control of treatment groups. Let's think about an extreme example here. What if our non-smokers were all 5 years old and our cigar and pipe smokers were all 85 years old? We don't have common support over the age, the control variable, or the confounder. We cannot, there's no comparable 5-year-old that smokes a cigar and pipe, and there's no in our data set, and there's no comparable 85-year-old that doesn't smoke in our data set, if that were the case. So that means we cannot reweight to make the distributions of X look the same. However, if these two assumptions hold, we can estimate the average treatment effect, and we'll get conditional independence. Expected value of the treated outcome, conditional on X, is independent of actual treatment. And same for the control group. Here's a graphic distribution of overlapping support. So what this is saying is, if this is our control variable, and this is the distribution of the control of let's call it the X variable, our confounder. If this is the distribution of the confounder for the control group, and this is the distribution of the confounder for the treated group, we cannot control people out here, or we cannot compare people out here to people down here. We can only compare here. This is our overlapping support. A little more on the CIA. The outcomes are independent of treatment assignment, conditional on observables. In other words, people are not selecting to be treated or not treated based on what the expected outcome is, regardless of their demographics. We should say conditional on their demographics. So I'm not selecting out of eating McDonald's, Big Macs, and ice cream every day because I expect I will end up having a heart attack, even though my health conditions now are okay. So as long as we can control for my health conditions, we should be fine. Let's look at another example. So the book talks about, are you more likely to survive the Titanic if you're wealthy, seated in first class? The argument is that it makes sense because first class was higher on the ship and easier to get out. However, women and children were given priority, so why might that be a problem? If that's a problem, how can we solve it? So here's our DAG for this example. Survival, being in first class, D, that's our treatment. We have women and we have children. So the DAG says that women and children are confounders because they're more likely to survive because people uh, put women and children into the lifeboats first, but they're also more likely to be in first class. So we have open backdoor paths for women and children. A quick, simple difference in means says that the expected survival rate of being in first class relative to non-first class is 35%. So if you are in first class, you have a 35% higher probability of surviving. But women and children were more likely to sit in first class, and they were more likely to be put in lifeboats. So let's use subclassification to control for these confounders. All right, we want to reweight our means in order to get a better estimate of this. So we're going to stratify the data into 4 groups: young males, young females, old males, and old females. This is somewhat arbitrary. Calculate the difference in survival probabilities for each group, the fraction that survived within each group. Young males are just going to be probably children, male children, versus older males. We're then going to calculate the number of people in the non-first class groups and divide by the total number of the non-first class population. And these are our weights. So just like we had in the age-adjusted mortality rate example, we're using the distribution of the number of people in each of the non-treated groups. We're using that distribution to reweight our means to make our treated survival rates look like we're reweighting by the control distribution. So we're going to calculate the weighted average survival rate using the strata weights as follows. So there's going to be 4 different Ks. Ks are the conditioning variables, in this case, child and women. We're going to sum over the difference in means for each of those groups, weighted by number of people in strata K divided by total number of people. And when we do this, we get the estimated average treatment effect of 16.1%. So we're controlling for age and gender. Our simple differences was biased because of the confounders.